Okay, so welcome back. My students, you had 6.1 and 6.2 finalized today. And these were the 4 formulas you had on your formula sheet for that. In addition, so I'll point out that these are, again, for my students. If you're not my student, I can't promise what you have. That's on the formula sheet that you're allowed to use for your final exam, which I highly recommend that you print out. I did make this available. I think I have it under reviews in the Canvas page. So if you go to Canvas and you go to reviews, this should be available. If it's not, I'll double check and make sure it's available later today. But then we also had that one formula from 6.2 that was to convert. You know what, I don't need to spell that out. Between the continuous rate and annual rate, APR. And that was that e to the k it's a terrible looking k, is equal to R1 plus R. R plus 1, 1 plus R, it's the same thing. But again, the idea here was that this is one growth factor, this is another growth factor. We're just setting 2 growth factors equal to each other. That's all this is. This is just line. This is just setting one growth factor equal to another factor. That's all it is. E to the k is the growth factor in that continuous model that Excel uses, that I said to my students that if we didn't use Excel, you wouldn't even be doing this at all, because there is no reason for us to use a continuous model as a QR student. We prefer much more standard models, which are these 4 things up here. Now, the k is the continuous rate. Why did it switch to blue? Did I hit blue and not realize it? Must have. So the continuous rate is the k, the annual rate, the APR, that's the R. And we also said that this is kind of like doing an APY, but instead of going from compounding monthly to yearly, it's like going from compounding continuously to yearly. So this R here is also known as an APY, and we're only able to go from the continuous rate K, excuse me, to the annual rate R. We are not capable of going backwards, and by not capable, I mean I haven't taught you how to do it. If you've ever had math with what we call natural logarithms, it involves something like that. But we're not going to show you how to solve those. That's pre-calc material. So if there's a homework problem or two, it won't be counted as graded. There might be like one problem on the final that has a two-parter, and I have to say skip the second part if that happens. I'm still setting it up, so I can't promise anything, but I know I've had that happen in the past. But I'd point out anything that you're supposed to skip ahead of time. All right, so what I want to do in here today is just practice using these formulas, mainly focusing on the first 4, since this is what we tend to do a lot more of going forward. But if I have time, if we can get to it before the hour's up, then we'll do another one of those. I mean, I say another one, but that's just considering the class before. If you didn't have me, it's not another one, it's the first one of the continuous to the annual. And this one right here, the continuous to annual, is interesting because you have just a baby step of algebra to do. You have to subtract 1 on both sides. So you plug this part in the calculator, then you subtract 1 and you're done. So what some students might say is, oh, okay, well, I'll just memorize it as this. E to the k minus 1 is equal to R. And yes, that is the same formula, and then there's no algebra to do. The red and the blue here are the same. It's just a matter of, this is blatant memorization of a formula in blue, whereas the red is a concept of setting one growth factor equal to another growth factor. This is a continuous growth factor. This is the standard growth factor, and that standard growth factor is what we've been using over and over and over. I must have left my email open. Yep, sure did. I heard a ding that you may not have heard. Actually, you probably did because it probably came from my speaker to my mic and you heard it on a delay. Fun stuff. So what I want to do, again, mainly focusing on these four, is throw a problem at you, but not necessarily, oh, we're going to do a problem with this one, then we're going to do a problem with this one, then a problem with this one, then a problem with this one. I'm going to do these in a complete random order so that we have to think about which one we need. All right, so let me give myself lots of space so we don't goof anything up. Example 1. Buddy Bob, classic Bob. I'm just trying to fix one more tiny thing. Move. There we go. All right, Bob. Bobby Bob. Bob has $45,000 currently. He invested some money to an account that compounds interest quarterly earning 3%. Sorry, I feel like I'm missing something. No, I have it all. All right. Bob's got 45 grand currently. He invested some money into an account that compounds interest quarterly, earning 3%. So it's 3% annually, but he's going to compound it quarterly, which means he gets interest every 3 months. There's 4 quarters in a year, 4 3 months in a year, 4 sets of 3 months, that is. All right. So if Bob invested 19 years ago, how much did he have time? So this is where we have to be very careful. A lot of people want to just assume, all right, we're going to do A equals P parentheses 1 plus RT, R raised to the T, or the R over N raised to the NT. A lot of people just always go for that one. But you have to pay attention to the numbers. When you get your answer, you have to make sure that it makes sense in the context of the problem. So you need to ask yourself, is this $45,000 the starting amount, or is it the ending amount? All right, Bob has 45,000 currently. Well, that sounds like a starting value, right? That sounds like a starting value inflection in voice. If he invested some money into an account that compounds interest quarterly, earning 3%, I got like a compound sentences here going on. And Bob go. And Bob invested 19 years ago. How much did he have at the time? So this doesn't say he put $45,000 in. That's what he has currently. We're talking about how much money did he have originally 19 years ago. We lost all our receipts. Our bank has changed hands more than once. So this data just doesn't exist anymore, maybe. So this is not a starting value. This is an ending value, which the letters in the formula sheet above, we tend to call that an A. So our rate of 3% means it's a 0.03 as a decimal place. 19 years, that's our T. But, well, how did we compound? Because we're going to be using one of these formulas. I'm not saying which yet. But some of them have an N, some of them don't. The question is, do we need it? All right, blah, 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 compounds. So we're compounding interest quarterly. So that's not annually. So we definitely can't use an N of 1. If we're compounding quarterly, that means that the N has to be, well, how many quarters are in a year? There's 4 quarters in a year, just like there's 4 quarters to $1. Now, again, the weird part is that that occurs every 3 months, and that can throw some people off. Is it the 3 or is it the 4? Sometimes you're using the 3 if you're trying to go if you're trying to prorate a cost from a quarter to a month, then you're dividing by 3. But when you're talking about a number of intervals in a year, it's 4, which is a much more common thing to use. So we have the A, the N, the R, and the T. Now we know the ending amount, which means we're trying to find the starting amount. How much did he have at that time 19 years ago? That's the starting amount. That's the unknown. That's the P. We don't know it. So we don't want to use any formula that has a P on the side of where we're plugging things in. So it's definitely not one of these two. APY is just converting one rate to another type of rate, so it's definitely not that one. It's got to be this one because we know the A, we know the R, we know the N, and we know the T. So that's the formula we're going to need to use. The third one. Now you might say, well, what if it was compounding annually? If it was compounding annually, you didn't give me that formula. Yes, I did. If it was compounding annually, you just make the n's ones, which means they don't even really need to be there. So again, I pointed out that some people may like to say, all right, well, we got this other formula, P equals A over parentheses 1 plus R raised to the T if it compounds annually. Now, I'm not giving you permission to add that to this formula sheet. I'm not doing that. I'm just saying that, yes, this is technically an additional formula, but it's so easy to drive because all you do is just derive, not drive, is just make the n's go away, and it's literally the formula. Because if the n's are 1, R divided by 1 is R, 1 times T is T. Okay, so we're going to put those four numbers into the formula. P equals A over, so that's 45,000. I don't know why I'm writing it so far to the right. What's happening? Still doing that. What's happening with my pen? It keeps jumping. Put it over here. Thank you. There's the A, which is the starting amount, all over 1 plus the interest rate of 3% is 0.03 divided by the N, which is 4, then raised to the NT, which is 4 times 19. All right, well, 4 times 20 is 80, so I can just subtract 4 to get that, and it's 76. If you don't like the way I multiply things, just put them in a calculator or do them your own traditional way. I know I mess with numbers in a weird way, but that's because numbers are weird. So we said 76. So 76 is the number of times that Bob has gained money. That's what this means. He gained money for 19 years, and he gained money 4 times per year, which means he gained money 76 times. It's the exact same thing as a number of payments that we talked about in class. Now, you don't really want to do too much simplification of this without a calculator. Things are going to get pretty intense quickly. So if you don't have a graphing calculator, you don't necessarily need one. A scientific calculator will get the job done, but a 4-function calculator is going to start giving you complications along the way. So 45,000, 45,000. I don't know that I've ever clicked that button that quick and it actually registered both. Divided by 1 plus 0.03 divided by 4. Close it. Then exponent, and the exponent's a 76. Remember I said you have to pre-multiply the exponents. If you put that 4 times 19, depending on your calculator, it's probably going to give you a wrong answer. And we end up with $25,502, and rounded to the nearest cents would be 83 cents. So that was how much he started with. Does that make sense? Well, given the context of the few examples I've given you, going from 25,000 to 45,000 with 3% interest over 20 years, that feels like it's in that ballpark. And again, you can't, say, oh, well, this answer should be 47,000 or it should be 42,900. You're not going to be able to make that kind of accurate assessment. What I'm saying is we shouldn't have, if we had 45,000 with this measly 3% over 20 years, it's not like we started with $100. If we got $100, that interest rate would have needed to be probably like 15, 20%, or the time would have needed to be like 50, 60, 70 years to see that explosion of money. This seems nominal. It might seem like a little more than you might expect, but it is correct. I can tell you that 3%, we're starting to get a little more money. 20 years is getting up there, but not a super long amount of time. And remember, the explosion is mainly based on your rate and time. Rate has a larger effect than time, in fact. All right, so another way, does it make sense? Well, first of all, this number, how much we started with, should be less than how much we ended with. And 25,000 is less than 45,000. So if I had done the wrong formula, I wish I'd done that in blue. If I had said, oh, well, let's go with A equals the 45,000 parentheses 1 plus 0.03 over 4 raised to the 76 after we did all the math, that would have been plugging it into this formula. But again, what I've done wrong here is that's a starting value but it's really supposed to be the ending value. 76. So if you type this out, let's see what happens. 45 grand. So the true nature of the blue one is this is 45,000 invested for 19 years at 3% quarterly. So again, this answer is wrong for the context of the problem. I'm just showing you how I can tell it's wrong. 79,000. How would we have started with 79,000, gained money for 19 years, and end up with 45,000? That does not make sense. So that would have been the wrong answer. If I said Bob starts with 45,000, how much does he have after 19 years with all of that other stuff? Then this would be the answer, and it would make sense, starting with 45 and ending with about 80. All right. So I just want to erase everything that was wrong. I want to erase everything that's wrong, not move it. All right. Part B. Part B. How much was free? How was much? How, this is being weird. How much was what I like to call free money, aka interest? I'm not asking for the interest year 1. I'm not asking for the interest year 5. I'm not asking for the interest year 19. I'm asking for all of the interest. And the total interest should be the difference of how much you have at the end and how much you started with. So that would be the 45,000 minus the $25,502.83. And you can feel free to use your calculator for that. 25502.83. And we get 19,497.17. So there's our answers. Interest, the free money, almost 20 grand. We started with about 25 grand. We got about 20 grand for free, giving us about 45 grand at the end. Just thinking in terms of nice, bigger numbers. All right, let's do another one. Bob invested, let's go with $7,000 to a savings account, earning 1.5%, compounds daily for 3 years. How much does Bob have when he withdraws it? When he withdraws everything? How much interest did he earn over 3 years? Now, what I'm going to do is I'm going to talk through this at first. I'm going to eventually point out which formula to use, and then I'm going to give y'all a couple minutes to try it out on your own. So I'll mute myself, let you try it, and then I'll come back and show the work. But when you do your work, when you get your answer, ask yourself if everything makes sense. $7,000 at 1.5% for 3 years. That's a low rate, that's a low time. You probably don't expect to see a lot of action in that. If you come up with an answer that was like 100,000, that wouldn't make sense. If you come up with an answer of 5,000, that wouldn't make sense. How would you start with 7 and end with 5? So obviously the answer should be bigger, but not too big. So this 7,000, that's how much he invested. So that's the start. That's the P. 1.5 says the R, if that decimal goes left twice, is 0.015. It compounds daily, so that means the N is 365. And then 3 years, that means the T is 3. So our starting value is 7 grand, our interest rate, our compounding interval per year, and our time are all laid out. If we have P, R, N, and T, going back to our formulas, well, we have an N that isn't 1, so this formula is out. We're not just trying to convert a monthly rate to an annual rate, or a daily rate to a month. My tongue's getting tied. Let me start that fresh. We're not trying to convert a monthly or daily or quarterly or semi-annually rate to an annual rate. We're not just interested in comparing one rate to another, so that's out. It's got to be one of these two things. Well, we know the starting value, which is the P, which means we have to use this one and not that one. We would use the one I'm circling right now if we knew the ending value. So we're going A equals P parentheses 1 plus R over n raised to the nt. All right, so you've got your numbers. Be careful. Your n and the t, don't forget to pre-multiply them. You're going to need to go ahead and know what 365 times 3 is. Then you can put everything in the calculator and get an answer that's, you know, $8,000, $9,000. I wouldn't expect it to be any more than that. It might even still be in the 7,000s. I don't want to spoil too much of the fun, but it shouldn't be 70,000. It shouldn't be 700,000. It shouldn't be 700, because that would be less. All right, so try that out. I'm going to give you 3 to 5 minutes. We'll come back and show it together. Alrighty, so let's see what we can get. So putting all the numbers in the right place, hopefully. We got our starting value of 7,000, so that should go here. You can use commas when you're writing this if you like. Sometimes if you're ridiculous with your commas, they might start looking like parentheses, so just be careful with your handwriting. And I know I'm saying that very hypocritically, but I can't help it. All right, then 1 plus our rate of 0.015. Because remember, 1.5, we can't put that number in this. It's got to be the decimal unless we're using Excel. Excel could handle the percentage. Then divided by the n, which was 365. Then raised to the n times t, which is 365 times 3 years. So the first thing we want to know is, what is 365 times 3? It's 1095. Now remember, that number, what that means is When you simplify that exponent, that means that we have gained interest 1,095 times. But the fact that we're gaining interest every day means that those interest amounts are teeny tiny, maybe a penny, maybe 2 pennies, maybe 3 pennies. I don't know, I'm not saying, but it's small. So, but the fact that we gain it 1,000 times means those pennies turn into dollars and maybe dozens of or hundreds of dollars. All right, so let's see what we get. 7,000. Again, you might have to hit times before the parentheses, so I'll show it that way. It just depends on your technology, your calculator. 1 plus, then the 0.015 divided by 365, close the parentheses, raise it to the 1095. Drum roll, let's hope we get an answer that makes sense. 73.22 and then 19 cents. Does that make sense? Well, I think so, in my opinion. This was a low rate, so we shouldn't be earning a ton of interest each year. This is a low number of years, so there's not a lot of years for that low interest to accrue. So we've gained about $322. I think that's in the realm of sensibility. First of all, we didn't go down. That would have been completely wrong if we were under 7,000. Second of all, we didn't get some extravagant number like 70 grand or 700 grand. It's 7 grand and some change. So I think that makes sense. Then the interest, the total interest, that is to say, is the end minus the start, which would be the 73.22.19 minus the 7K, which I think is pretty obviously $322.19. So not nearly as much free money, but that's because Bob is in a lower rate and for a lower amount of time. All right, let's try a third one. Example 3. Bob borrows $19,500 to buy a brand new sedan. A 2020 Civic with not really any options. Maybe a 2019. Brand new can be a year old. I mean, that's good enough, right? So Bob borrows $19,500 to buy a brand new sedan. Now his loan will compound interest monthly at a rate of, let's say, 1.9%, because Bob's got really good credit. I just talked to a friend of mine who just got a car loan at 1.9% for, I think, 5 years the other day. So we're going to go with his loan for 5 years. Now, however, not however to anything up there, just however, Bob is going to let the interest accrue the entire loan and only pay it off, only make any payment, only make the total payment at the end. This is not how car loans work, FYI. I'm just giving you kind of a bridge. So Bob borrows this $19,500. So he didn't get a traditional loan. It sounds like he borrowed it from his mommy or his daddy or grandma or friend, whatever. And they said, all right, well, I'm going to charge you 1.9% a year, and it's going to be for 5 years, and we're going to compound it monthly like most car loans do, like most loans do. But instead of Bob making monthly payments, which again would complicate the math, it'll be a crazier formula we'll get into in chapter 9. So don't worry, we'll get to the true version of this problem later. But we're just going to say we're going to pay it off all at once. So we're just letting the interest build and build and build and build and build, which is a bad idea. And then at the end of the 5 years, we've been making killer investments, and now we got 100 grand in our pockets. We're like, all right, well, let's pay the loan off now. Again, this is not how car loans work. I just want to approach this from a different angle. Instead of a savings perspective, a loan perspective. So the interest in this situation won't be money you get for free, but money your mommy, your daddy, your friend, or whoever would get for free. So how much will Bob owe at the end, and how much was interest? So again, in reality, you'd be making monthly payments. The formulas are a little bit more hectic. And in fact, I'm going to show you the formula you would use. Loan payment formula right here. So we'll get to this in chapter 9, but for now, avert thine eyes. So Bob borrows $19,500. Is that the starting value or is it the ending value? Well, that's what he borrowed at the start, right? So that's the start. The start is what we traditionally call P. His loan will compound interest monthly, so that says that the N is 12 at a rate of 1.9% for 5 years, which says that the R as a decimal is 0.019, and the T is 5. We got our P, we got our N, we got our R and our T. It's time to party. I know there's no N in party, but PRT. Bear with me. All right, so again, Bob is just going to pay off all this entire car and the interest that accrued over a long time, which means he's paying more interest than you traditionally would. But again, this is not a traditional problem. So how much will Bob owe at the end? So how much will Bob owe at the end? That's what we traditionally are calling A, the future value. How much is interest? Well, that'll just be that easy subtraction, but let's do that later. So what formula do we think we need if we know the principal, the N, the R, and the T? Oh, I forgot to undo all that. Okay. Well, once again, we're not just converting from an annual rate to a compounded rate or a compounded rate to an annual rate. So that's out. So it's one of these three things. What do we know? We know the starting value. This is the ending value, so we can't use this formula because we don't know the ending value. We know the starting value, so it's one of these two. It's got to be one of these two. But we said that we compound monthly. This top one is only for annually, which is in being, 1. So that formula is out, which means we're actually going to use the same formula as last time. So A equals P parentheses 1 plus R over N raised to the MT. So the same exact formula as last time. So I'm going to give you, once again, 3 or 4 or 5 minutes to try those out. I'll come back, and hopefully our answers align. All right, so let's see what we can get. First of all, if you wanted to kind of try and predict what your answer might look like, 5 years, 1.9% interest. I mean, we're in the ballpark of the numbers last time. The principal is about 3 times as much. So maybe I expect the interest to be in the ballpark of 3 times as much, maybe 5 times, maybe 2 times. And again, I'm just spitting out ballpark numbers, but we're not going to expect this to turn into a $35,000 car over 5 years or a $80,000 car over 5 years. I'm going to say no more than 22,000 and, plus 23,000, 21,000, somewhere in that ballpark, but let's find out. So our principal was the 19,500. Open parentheses, 1 plus. The R was 0.019. You find a lot of car loans that are like 2.9, 1.9%. Then divided by the N, we compound in monthly, so 12. Raised to the NT, which is 12 times 5. And again, you really want to see that 12 times 5 being a 60 before you put it in your calculator for most, if not all of us. Like so. And then we just crunch away 19,500 times 1 plus 0.019 divided by 12. Close it, raise it to the 60th power. And we get $21,441.74. So that was the price of the car with interest. A W with a circle means with, so that's price with interest. In other words, the future value A. Now, I'm not saying that the car has appreciated value. I'm saying that the price you have to pay for this car, doing this lump sum payment at the very end, which literally no one does, would be $21,441.74. This is just a scenario where maybe you borrowed some money from a friend and you were without a job for a very long time, and then finally you got your job and the money starts coming in quick and you just want to pay this loan off immediately, and your friend was charging you traditional interest. Now, some friends wouldn't do that. Some friends understand that you still need to be making a little bit of money when you offer a nice gesture. And I'm not telling you how to do any loans with your friends. I'm just saying that some people will do this. Some people will just say, all right, well, give me whatever you borrowed plus $500. When it's a friend, you don't actually have to have true math behind it. But at the same time, there can be friends that think they're getting a deal because, oh yeah, I'll just pay my friend one extra payment, and maybe that's more than the interest would have been if you actually used a traditional system. I don't know. It could be anything. So this price makes sense. So our $19,500 car ends up costing us roughly $21,500. You can see the dollars and cents there, meaning that the total interest, being the end minus the start value, would be the 21,441.74 minus the 74, it looks like a 1, minus 19,500. So we can just go minus 19,500. And we get $1,941.74. There we go. There's our total interest. That's how much money Bob's friend made for doing this weird loan that, again, is not how things would normally be done. I don't know how many times I have to say that. If you make this instead of a 1.9% loan, let's change this to I'm not going to show every single layer of detail. I'm just going to say, what if this had been a 5.9% loan? So I can go back to this previous problem. I can just hit second enter twice to call back that formula, and I'm just going to go and change the 0.019 to a 0.059. So this is a significantly higher loan. Maybe Bob's credit with his friend sucks, so now he's got to pay a higher interest rate. Now that 6% interest has a larger effect on how much total interest Bob's going to pay over that, and it ends up being $26,172, meaning that he pays his friend, by doing this weird balloon payment system, $6,672, and that's the money that Bob's friend would get for free for doing this upfront loan. So you can see how these interest rates can greatly affect you. And that's why we want to get your credit scores as high as possible. by the end of the semester or start you understanding how to do that. I can't just get your credit score as high as possible by the end of the semester. It takes a long time. It's a slow and steady crawl. And there's a lot of misconceptions in that too, but I'll be talking about that in the QR class. All right, next example. Bob invested into an account that earned 5% compounded daily. Bob is curious, his effective annual yield, aka the annual percent yield. Now, just because I'm giving you both versions of that phrase in this example doesn't mean my math lab problem or a test problem has to. That's why I'm trying to make sure I always repeat that they are the same thing. EAY is APY. So Bob is curious as to what his effective annual yield would have been, is, that he knows what rate he would have needed to invest at to match his growth if it only compounded annually. Again, I'm being very literal with the phrasing of this stuff. I could have told you that Bob invested $50,000. It would have been completely unnecessary. I could have told you that Bob invested $50,000 for 40 years. Both of those numbers would have been completely unnecessary because I didn't ask for his ending value. I didn't ask for an interest. I asked for what his APY is, which the APY formula is only dependent on the rate and the number of times it compounds per year. There is no principal in here. There is no t in here. The t is always a 1 because this is over 1 year exactly. So we need this formula, 1 plus r over n raised to the n, and then a minus 1. So APY equals 1 plus r over n raised to the n, then a minus 1. So again, Bob's goal here is say, I know I put my money into a 5% account that compounded daily, but what if someone else is offering accounts only that compound once per year instead of 365 times in a year? He wants to know what rate he would need in that account to match his growth. Because if he gets a 5% compounding annually, he won't match his growth. He won't get as much money. It's going to need to be a little more. So what's the effective rate? All right. Well, that's parentheses 1 plus, that's 0.05. Divided by, if we compound daily, that's an n of 365. Then raised to the n again, so that's 365, and then there's a minus 1 outside. We really don't need to do anything in this calculator step by step. We can generally type these out all at once. Now, your calculator might work different than mine, which is why I've been saying you've got to practice this stuff. Watching me do it is not practice. Do it yourself, because you will make mistakes. You will then hopefully learn from your mistakes, and you will do it right. You know how I know this? Happened to me. It's how I've learned anything in my life. It's by doing it wrong and then doing it right. My house can attest to that. All right. Parentheses, 1 plus 0.05 divided by 365. Close it, raise it to the 365. Now I mentioned if your calculator makes the exponent a little higher and a little smaller, you might have to hit the right arrow to get out of that. Mine, I don't. But if you get an answer that differs from mine, that's probably what happened. So 0.05, 1, 2, blah, 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 blah. And we need a lot of these at first. 6, 7, I'll go all the way to the 4 and the 9. You can write the whole thing if you really want to, but we need that to be a percent, so you just move the decimal right twice or you multiply it by 100. And that's why I did not round that too much, because this is the thing that usually gets rounded to 1 or 2 places. And I didn't specify, but I'll say it in a second. So as a percent, this would be 5.1267 blah, blah, blah percent. Let's take this to 2 places. This will be 5.13%. That's his effective rate. So by him gaining it's a 5% rate. So you'd think you'd get 5% over a year, but because you compound more frequently, you get a little more. And that little more being that extra 0.13. So what this means is if Bob's system changes and they start offering accounts that compound only once per year, he would need to earn 5.13% at once per year to match the 5% compounding every single day. No, it's not a very large increase, but it is enough to lose some dollars, maybe lose tens or hundreds of dollars if you have a large deposit in here. The larger the deposit, the bigger the effect. There's something else I wanted to say. I lost my train of thought. That's fine. That's good enough. All right, we'll do one more and we'll call it a day. We'll let everybody go since it's about to be a holiday. So example 5. We haven't talked about Jane. Let's talk about Jane. Bob and Jane, good friends. So Jane is going to deposit as much money as needed today to eventually have $500,000. She is going to invest to an account, see a mutual fund, can earn 8% compounding monthly. 35 years. How much does she need to deposit? So Jane has a goal. She wants to have $500,000 in this account by the time she hits, I don't know, retirement age. Or maybe Jane is 2 years old and she wants to have this when she's 37. If Jane's 2 years old, she's kicking butt at math knowing to do all this stuff. And I tell you what, man, teach your kids this stuff. If you got kids, teach them as young as possible. That whole Starbucks cup of coffee thing, if you got a 16-year-old, get them started now. Get them started at 18. That way they can be millionaires by the time they're 67, 68 without even much effort. Because we've already seen the effect of waiting 10 years and waiting 10 years. And as someone who may have waited 10 years, who didn't get told this when they were 18, I'm trying to help as many people as I can get it right. All right, so Jane is going to deposit as much money as possible to eventually have $500,000. So $500,000 is our known dollar amount, but is it the start or the end? Well, I think with the phrasing, it's very clear the end. This 8% says the R is 0.08. We're compounding monthly, so the N is 12. We're doing this for 35 years, so that's 35. How much does she need to deposit to make this happen? So how much does she need to deposit? That's the P. We don't know the P. Now, because we have an N, we definitely aren't going to use a formula without one, which says that very first one is out. We're not converting between a rate of compounded monthly to a rate compounded annually or anything like that. So there's no effective rate, there's no APY. So it's a matter of which of these formulas with N is it? Well, this one, we know the starting value, which was actually the question. We don't know what the starting value is, so that's out. And we need to use this one because we know A, we know the ending amount, we know our goal of $500,000. So this is our formula. P equals A over parentheses 1 plus R over N raised to the NT. So this would be 500. Oh, that's right. I said I was going to give you a minute or two. Try it out. See what you can get. When you get your answer and ask yourself if it makes sense, it should be less than 500,000. Now, this is a solid rate, and this is a solid amount of time. So this money's probably doubled a couple times. If you get an answer of like 400,000, that doesn't sound right. If you get an answer of 300,000 or maybe even 200,000, that doesn't sound right to me. So maybe an answer of 50, 60, 70,000 will do the job. Maybe that's too small. I don't want to spoil too much, but just try this on your own, plugging the numbers in, remembering to pre-multiply your exponent, and see if you get an answer that makes sense. All right. Right. So we have our 500,000. I don't know where that 3 came from. Divided by parentheses 1 plus the 0.08 divided by 12, raised to the nt, which is 12 times 35. You need to see what 12 times 35 is. It's 420. That's 500,000 divided by parentheses 1 plus 0.08 over 12, raised to the 420th power. So then we just type that out, plus 0.08 divided by 12, close it, raise it to the 420th power. Drum roll, 5-digit number, $30,688.87. That's how much we would need to deposit now in order to have $500,000 35 years later if we manage to get an account that constantly returns 8% interest. Again, real world, your rates change every single day when you're investing. One year you might have an average return of 30%. One year you might have an average return of negative 35%. The next year you might have a return of 72%. The next year you might return 2%. There are ways to calculate the average return at the end of your 35 or 40 years of investing. It's not a pretty formula, but it is out there, and I'm not going to teach that in here because it's not a pretty formula. And if you've seen the things on the formula sheet, if I'm not saying that those aren't ugly enough to show you, imagine what this one looks like, right? But anyways, if you're doing this kind of weird retirement plan or supplemental retirement plan, Jane's going to need about $30,689 so that she'll have $500,000 later. Now, hopefully Jane has still got another pile of money she's continuously adding to, substituting that Starbucks coffee and making coffee at home just to slowly add to the pile, and then maybe have $1 million or $1.5 million. This is just extra. This is 30 grand Jane happens to not need, right? Because how many of us don't need 30 grand? Ha 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 ha. But Jane has 30 grand to spare. She puts away, tucks it under the digital mattress that is a Fidelity account or an Acorns account or a E-Trade account or a Robinhood account, and she invests it in S&P 500 or NASDAQ or something else that their financial advisor told them to do, or whatever independent research Jane has done. And boom, $500,000 just with expected returns. Again, expected, not guaranteed, expected. This is about how things usually work when you invest for 30, 40 years, but nothing's guaranteed. Past results do not dictate future results. This is not financial advice. This is for educational purposes. No suing is allowed. All right.